Hello friends, welcome back in today's lecture. I am Dr. Milind Meshram, working as an assistant professor in the Department of Chemistry at Chem College, Nashik. So in the last lecture we have seen the carbon-carbon disconnections. Alright, so we have seen the target molecule which contains the trans-alkene. So we know the trans-alkene can be obtained from alkyne by employing the Birch reduction, isn't it? So today we will discuss the carbon-carbon disconnections. We will take an example that target molecules cis-alkene is present. So as I mentioned it before, cis-alkene can be derived from alkyne by employing a linear catalyst. Okay. So let us have the target molecules which is having the cis-alkene. Alright. So this is our target molecule. So which is having G-alkene in cis-alkene. Now we know this G-alkene can be derived from alkyne by using linear catalyst. So let us do this FGR. So let us put this retrosynthetic arrow. So FGR so this alkene can be converted into this alkyne. Okay, this is our target molecule, alkene, cis-alkene. So this is our alkyne. So as I have discussed in the last lecture, this terminal alkyl group can be installed by substitution reaction. Okay. So this G-alkene can be obtained from alkyne. Okay, by using linear catalyst. Okay. So here we have done the FGF functional group interconversion. So this G-alkene can be transferred to this alkyne. Okay. So now in the next step, so we have this carbon-carbon disconnection. Okay. So let's put this line to disconnect this. So we will get this two fragments. So one carbon will acquire this negative charge and other will have this positive charge. Okay. So let us translate this synthon. This can be translated to this alkyne. Okay. So hydrogen we can add, and this, so this synthon we have already discussed. Okay. So this can be translated to its epoxide. Okay. So this epoxide is a good electrophile. So now we have this this substituted alkyne. Okay. So further we can disconnect this bond. Since this substituted alkyne can be derived by using substitution reaction. Okay. So we have one more carbon-carbon disconnection to get this. One will have this bromide and one will have this hydrogen. So it will be acetylene. Okay, and these are the chemical equivalents. Here I have not written the synthon. Okay, so I have directly written chemical equivalents. So naturally this will acquire, this carbon will acquire this negative charge and partial negative charge, and this will acquire partial positive charge. So since this carbon is having positive, so we can add bromide. Okay, here hydrogen. So these are the chemical equivalents. So what we have done, so in our target molecule there is a presence of G alkene. So we know this G alkene can be obtained from alkyne by using Lindlar catalyst. Okay, so we have just applied FGR, functional group interconversion. So we have converted this alkene to alkyne. So it's a, then in this case it's an obvious disconnection. Okay, because when you disconnect this bond, so you will end up with the readily available epoxide and this alkyne. Okay, so this is the just simple substitution reaction with the help of strong base. Okay, so then after having these two synthons, okay, so this disconnection will end up with this epoxide and this alkyne, substituted alkyne. Okay, so again this substituted this ethyl group can be installed by substitution reaction. Okay, this ethyl group, okay, this ethyl group can be installed by using substitution reaction of this alkyne. Okay, so after having these carbon-carbon disconnections, we would get these chemical equivalents. Okay, this is all about the retrosynthetic analysis for this cis alkene. Okay, so let us have its forward synthesis. Synthesis, we have the acetylene starting materials and ethyl bromide. Okay, so when this acetylene reacts with sodium amide, strong base. Okay, so this acetylene is acidic, having acidic proton, so it requires the base like sodium, suitable base like sodium amide. So it will generate sodium acetylide. Okay, this is the sodium acetylide. That means this carbon will have partial negative and this is partial positive. So in the next step, this is the substitution reaction. So we have ethyl bromide. Okay, so it will this acetylide So we will get this product substituted alkyne. Okay. So when you treat this acetylene with sodium amide and then treatment with ethyl bromide, we would get this substituted alkyne. Alright. Then in the next step, the treatment of, in the first step, treatment of sodium amide. Okay. The treatment of sodium amide will extract this proton. Okay. Then followed by the treatment with this epoxide. Okay. This epoxide is acting as an electrophile. Okay. It is electrophilic in nature. So this is also a substitution reaction. So again this sodium amide will extract the proton and attack at this carbon atom. Okay. So we will get this product this product. Alright, this is the alkyne. Then in the next step, the treatment of this alkyne with Lindlar catalyst we will get this target molecule. Alright. So, in the first step, the treatment of acetylene with sodium amide gives this sodium acetylide, which on treatment with ethyl bromide, it gives the substituted alkyne. Then again treatment with sodium amide and followed by the treatment with epoxide. This ring will get open and which leads to the formation of this alcohol. Okay. Then this alkyne, when you treat with a Lindlar catalyst, that alkyne get converted into G alkene. Okay. So this is our target molecule. So this is how we can generate the cis alkene by using this alkyne chemistry. Okay. So let us have the another example. Now we will see the carbon-carbon disconnection where we will have the 1,2 disconnection. Okay, 1,2 disconnection. So let us have this example. The retrosynthetic analysis. Retrosynthetic analysis let us draw it again. So this is our target molecule. So this is our target molecule. When you spot this, when you look at this molecule, you will observe there is a presence of ester group, okay, and there is a ethyl substituents, okay. So it is the obvious disconnection, 1-2 disconnection, 1-2 carbon-carbon disconnections, okay. This ethyl group can be introduced by alkylation, okay. If you do, so let us put this retrosynthetic arrow, 1-2 disconnection, this carbon-carbon disconnection, okay. So when you draw this line, so we will get this. This ethyl fragment and other, we would get these 2 fragments. So this fragment will acquire the negative charge, okay. So let us translate this synthon. So since it is this ethyl, this group is having positive charge, so we can add bromine over here, and here we can add proton, yes, we can add hydrogen. So it is the carbanion, okay. So this is the retrosynthetic for this particular ester, okay. So when you look at this ester, so you would think about this 1-2 carbon-carbon disconnection, okay. So this is the obvious disconnection. So this, since this ethyl group can be introduced by using substitution reaction, means this ethyl group can be introduced by alkylation reaction, okay, using carbanion chemistry. So let us have its forward synthesis. In the end, we have got this ester, okay. So when you treat with base, so when you treat this ester with base, then followed by this bromoethane, which leads to the formation of this target molecule, okay. So this is the simple substitution reaction, okay. So there base will attract this proton, it will generate this carbon ion, then okay. So in this way we will get our target molecule. So this is all about the today's topic. So in the next lecture we will see more problem based on this carbon-carbon disconnection. Thank you.